This is a lecture on solution chemistry. Let's begin. Stirring and heating increases the rate at which a solute dissolves. A cube of sugar in cold tea dissolves slowly. B, granulated sugar dissolves in cold water more quickly than a sugar cube, especially with stirring. Granulated sugar dissolves very quickly in hot tea. You've all seen that before. Much of what we're going to be doing here should be extremely familiar to you, with the exception of maybe some of the calculations. Stirring and solution formation. If a teaspoon of granulated sugar, sucrose, is placed in a glass of tea, the crystals dissolve slowly. If the contents of the glass are stirred, however, the crystals dissolve more quickly. The dissolving process occurs at the surface of the sugar crystals. Stirring speeds up the process because fresh solvent, the water in tea, is continually brought into contact with the surface of the solute, the sugar. It's important to realize, however, that agitation, stirring, and shaking affects only the rate at which the solid solute dissolves. It does not influence the amount of solute that will dissolve. An insoluble substance remains undissolved regardless of how vigorously or for how long the solvent-solute system is agitated. What else speeds up the solubility process from that one example? Very important. Temperature and solution formation. Temperature also influences the rate at which a solute dissolves. Sugar dissolves more rapidly in hot tea than in iced tea. At higher temperatures, the kinetic energy of the water molecules is greater than at lower temperatures, so they move faster. The more rapid motion of the solvent molecule leads to an increase in the frequency and the force of the collisions between water molecules and the surface of the sugar crystals. What is the relationship between a gas solute and a liquid solvent? Is there some kind of connection relative to a solid solute and a liquid solvent? Is there a similarity? Is there not a similarity? Particle size and solution formation. The rate at which a solute dissolves also depends upon the size of the solute particles. A spoonful of granulated sugar dissolves more quickly than a sugar cube because the smaller particles in the granulated sugar expose a much greater surface area to the colliding water molecules. Remember, the dissolving process is a surface phenomenon. The more surface area of the solute that is exposed, the faster the rate of dissolving. So what we have now, we have agitation, we have temperature, and we have surface area. These are the currently these are the things that affect the rate at which something is dissolved, not the amount of solute that can be dissolved, but the rate at which the dissolving takes place. Just like in a chemical reaction, you have a rate of reaction, but if the reaction is not going to occur because of some electronic inhibition, then it doesn't matter what you do to it, it's not going to react. So rate of reaction, rate of dissolving is different from whether or not something is soluble or insoluble. So what actually causes something to be sustained in solution, to be held in solution, to stay dissolved? What causes that phenomenon to occur? Well, it's going to be something called solvation, and we're going to get into solvation momentarily. But remember that solvation is the surrounding of a molecule, surrounding of a solute molecule. In a saturated solution, a state of dynamic equilibrium exists between the solution and the excess solute. The rate of solvation, there it is, dissolving, equals the rate of crystallization, so the total amount of dissolved solute remains constant. So solvation is the surrounding of the individual solute particles by water, fertilizer runoff. Most farmers use fertilizer that contains salts of one or more of three essential elements essential to plant growth: potassium, nitrogen, and phosphorus. When more fertilizer is applied than the soil can absorb, rain washes off the excess salts. Not only is this economically wasteful, it is hazardous to the environment. The water containing these dissolved salts flows into streams and rivers, where the salts contribute to the eutrophication of the water. Eutrophied waters are rich in nutrients but deficient in dissolved oxygen. Signs of eutrophication include overgrowth of water plants, algal blooms, and bad odors resulting from the growth of bacteria that do not need oxygen. In recent years, the problem of fertilizer runoff has lessened with the introduction of slow-release nitrogenous fertilizers. Many farmers have also adopted new methods to reduce runoff. In my hometown back in the United States, this was a major problem in the 60s and 70s, especially relative to horse farms and large farms that grew hay and alfalfa, etc. Liquids that are insoluble in one another are called immiscible. A thin film of oil spreads over a water surface. Light rays bent by the film create patterns of color. B, vinegar, which is water-based, and oil are immiscible. You can't really particularly see the oil in the water or the gasoline in the water, but it's very obvious if you ever see it. Changing the temperature usually affects the solubility of a substance. Something to note here, look at sodium chloride. Sodium chloride, of all of these salts, has a very small change in solubility in grams per 100 grams of water between the temperatures of 0 and, let's say, 80 degrees, which is pretty unusual. Describe what happens to the solubility of potassium nitrate as the temperature increases. It's going to increase. B, which substance shows a decrease in the solubility as temperature increases? Which substance exhibits the least change in solubility? And C, suppose you added some sodium chloride to a saturated solution of sodium chloride at 20 degrees Celsius and warmed the mixture to 40 degrees Celsius. What would happen to the added sodium chloride? Mineral deposits form around the edges of this hot spring because the hot water is saturated with minerals. As the water cools, some of the minerals crystallize because they are less soluble at the lower temperatures. Note that potassium nitrate is extremely soluble in water at high temperatures and extremely insoluble relative to others at low temperatures. So how much of that crystalline material is potassium nitrate? A supersaturated solution crystallizes rapidly when disturbed. The solution is clear before a seed crystal is added. Crystals begin to form in the solution immediately after the addition of seed crystal. Excess solute crystallizes rapidly. A supersaturated solution is a solution in which more solute is dissolved than is allowed by nature. And then you can do, if it's undisturbed, you can do this kind of, there's solubilities of substances in water at various temperatures. You can do this kind of neat experiment with the supersaturated solution of potassium nitrate. Notice the gases. What happens to the gases as you increase the temperature? Look at 100 degrees and look at those three gases. That's pretty amazing, actually. So Rainmakers. U.S. scientists Vincent Schaefer, Irving Langmuir, and Bernard Vonnegut carried out the first successful rain-making experiments. They knew that water vapor in the atmosphere condensed around tiny nuclei, sand particles, etc., such as particles of soot. In 1946, Schaefer produced snow by dropping dry ice, solid carbon dioxide pellets, into clouds. A year later, Vonnegut discovered that silver iodide particles also serve as precipitation nuclei. Since that time, seeding clouds with silver iodide has been the standard method. So rain can be made despite what Burt Lancaster might have, the character that Burt Lancaster played in The Rainmaker might have been alleged to have done. Pressure is a factor in the solubility of a gas. In a sealed bottle, both the pressure of carbon dioxide above liquid and the concentration of carbon dioxide in the liquid are high and equal. When the cap is removed, the equilibrium is disturbed. The pressure of carbon dioxide gas above the liquid decreases and carbon dioxide bubbles out of the liquid. You've all seen this when you go to the store and buy a bottle of soda and you open it up and it's warm. It bubbles out. Amazing. And the soda all comes out and it makes a complete mess. But if you open up a cold bottle of soda, much less carbon dioxide will come out of solution. And it will stay fizzy longer. Nothing like making a flat bottle of soda by opening it when it's warm. Your blood transports oxygen and other nutrients to cells throughout your body. It also picks up discarded waste materials from cells and carries them to your kidneys. Kidneys have the important job of filtering potentially toxic materials from blood and excreting them in urine. The body's entire blood supply passes through its two kidneys approximately every 45 minutes. Should the kidneys fail to function, life-threatening poisons would build up in the body. So always take care of your kidneys, drink plenty of water, always keep hydrated. Your kidneys need to filter the water out of your body, and your brain is mostly water and fat. So it's good to have some fat in your diet, and it's good to have a lot of water in your diet. So water and fat, much more important than many people would think. In that case, the treatment is usually dialysis, a procedure for cleansing the blood outside the body. Comparing and contrasting what are some similarities and differences between the way kidneys work and hemodialysis. A tube connects a patient to a dialysis machine. The machine pumps blood from a vein, circulates it through a dialyzing bath, and returns it to another vein. So, how long before you drink a glass of water is there a buildup of waste material that come out of the kidneys that has to be emptied from the body? Interesting how quickly the kidneys will filter out the water. And why does water come out of the kidneys with the waste material? Well, it has to be essentially, literally, washed from the body. The salts have to be dissolved in something. Here's the filtering apparatus, a nephron. Millions of tiny processing units called nephrons filter blood through a network of capillaries. The collecting duct carries toxic materials such as urea to the ureter for excretion, and then it goes out the urethra. So the ureter is between the bladder and the kidney, and the urethra is between the bladder and expulsion. Here are the parts of a dialysis machine, and I will speak as long as it's on. Semipermeable membrane, that's the red, and then you have the red blood cells. You have the waste material. You have the pump, blood pump, dialysis bath, white blood cells. There's the white red blood cells. used dialysis solution, semipermeable membrane. You have used dialysis solution. There's a platelet, etc. So the blood is the red, and that's going through this semipermeable membrane where the waste material can go from the blood out through the semipermeable membrane, but it doesn't lose some of the important ingredients. The tubing in a dialysis machine is a semipermeable membrane that allows particles to flow through it in both directions. The net flow is from the side with the higher concentration to the side with the lower concentration. Large particles such as platelets and red and white blood cells cannot move through the membrane and stay in the blood. Smaller particles of waste materials pass through the membrane into the dialysis solution. So here you have the dialysis machine and the explanation of the dialysis machine. I'm going to speak until this stops. Even with dialysis, if your kidneys stop working, and you can work and function on one kidney, oftentimes in families, when you have the loss of a kidney, you can donate one to another family member. Adding fresh dialysis fluid and removing the used solution containing water materials maintains the concentration of the dialysis bath. Comparing and contrasting. What are some similarities and differences between the way kidneys work and hemodialysis? Both use a semipermeable membrane to filter waste products from the blood. The process must occur at regular intervals, every 45 minutes in the kidneys and 3 times a week with hemodialysis. In hemodialysis, the cleansing of the blood takes place outside the body. So there are similarities and differences. And you can only do this for so long because it's just such a trauma on the body, because the human body, again, filters it every 45 minutes, where you're taking much longer if you're doing hemodialysis. Blood is a solution, a colloid, and a suspension, all at the same time. Blood contains gases, ions, and nutrient molecules in solution. It also contains biologically important particles, protein molecules in colloidal dispersion, and cells in suspension. For your body to function properly, solutes in blood must be kept at the right concentrations. Many of your organs participate in this process. The liver and pancreas are responsible for regulating the concentration of sugar in your body, while kidneys keep the concentration of dissolved waste products in your blood at a minimum. Here is an illustration. Solution A is concentrated, so you have more solute particles relative to water particles, and then the dilute solution, solution B, you have more water particles. And here is pure solvent A, higher vapor pressure, and then the solution containing non-volatile solutes, and you have the corresponding lower vapor pressure. There you have a picture of the solute molecules and then the corresponding solvent molecules. Here I have a variety of pictures that explores the reason why things dissolve, from hydrogen bonding to ion dipole, dipole-dipole, ion-induced dipole, dipole-induced dipole again, dispersion. This is reminiscent of material that we learned a little while ago, but very important when you're talking about the solubility not only in water but in other solvents. The solute-solvent forces make new structures, order, in the solution, but the solute breaks up the structure, order, that the liquid solvent may already have. So based upon the hydration shells, there can be order in the chaos of solubility. Very important concept, not only in science, but also in philosophy. Here I have water, methanol, and a solution of water and methanol. Methanol is miscible in water to a certain degree, but you can see there's much more hydrogen bonding in water than in methanol. Here is soap molecule, soap molecules immersed in grease. Some dissolution processes are quite complex and depend on different sides of a molecule doing different things, such as in the case with the action of soap detergent on a grease stain. So the polar end of the soap molecule versus the nonpolar end of the soap molecule relative to the solubility of grease, and which end of the soap molecule will do the dissolving. Solids and gases make solutions. One possible method of storing hydrogen gas for fuel is by taking advantage of its solubility in noble metals. And noble metals such as gold or platinum do not react with really very many chemicals, so they're called noble metals, such as the noble gases are also unreactive with other elements. So the noble gases. Here's hydrogen is dissolved in platinum. Here I have brass, copper, and zinc, as opposed to carbon, steel, carbon, and iron. Solid solutions, particularly of metals, are sometimes called alloys. Those are also solutions. We understand much of the dissolution phenomena through its energetics or thermodynamics. The change in enthalpy, H is enthalpy, internal energy, that's listed there. And we have figure 14, particle concentrations differ for dissolved covalent and ionic compounds in water. 3 moles of glucose dissolved in water produce 3 moles of particles because glucose does not dissociate. So that is A for figure 14. It's glucose does not dissociate. It dissolves, but it does not dissociate, but it does dissolve. 3 moles of sodium chloride dissolved in water produce 6 moles of particles because each formula unit of sodium chloride dissociates into 2 ions. So you have twice the number of moles of a salt, a binary salt, such as sodium chloride, where you only have 1 of each, as opposed to potassium or calcium chloride, where you have 3 ions, such as this. 3 moles of calcium chloride dissolved in water produce 9 moles of particles because each formula unit of calcium chloride dissociates into 3 ions. So that's C, that's calcium chloride. Here is someone is spreading salt on ice. That's going to depress the freezing point depression. And because it's used on the road, it's used for road safety. If you live in a northern latitude, you're going to appreciate that fact. Another colligative property, which is important in many biological processes, is osmotic pressure, the tendency for solvent to flow through a semipermeable membrane from a region of low solute concentration to a region of higher solute concentration. Osmotic pressure helps regulate the movement of fluids across cell membranes. Cells remain healthy as long as they are continually bathed in an isotonic medium, which maintains the correct osmotic balance between the inside and outside of the cell membrane. We talked about kidneys and how they function relative to filtering the blood. It filters using the colligative property of osmosis so that the waste material can permeate the semi-permeable membrane, while the other material, such as blood cells, will not leave the blood, only the waste products. Physicians make use of osmotic effect to treat patients with kidney failure, as we looked at before. Afflicted individuals undergo dialysis, a process in which the blood is circulated through a machine equipped with a semipermeable membrane. In the machine, osmotic pressure is used to separate waste materials from the blood. We spent a lot of time looking at that particular process. This shows concentration, a molal concentration, 0.5 moles of sodium chloride, 0.5 moles of sodium chloride, 29.3 grams in 1 kilogram of water. So you take 1 kilogram of water and you put in the solute. Okay, this is going to be a 0.5 molal solution, as opposed to putting the solute in and raising it up to 1,000 milliliters. That would be 0.5 molar. So molal is when you put the solute into 1 kilogram of solvent, and molarity is when you put the solute in first and then dilute it up to 1,000 milliliters of water, producing 1,000 milliliters of solution. A type of concentration is mole fraction, and this is what the mole fraction is. What fraction of the complete solution is the solute, and what fraction is going to be the solvent, and they have to add to 1. We'll see that a little bit later. Here are some constants for freezing point depression. Water is 1.86, you'll see that a lot. Benzene is 2.53, etc. Here are the boiling point elevation constants. Water is 0.512, benzene is 2.53, acetic acid is 3.07, and you'll see those a lot. Here's the boiling point elevation and freezing point depression equations. Delta TB is the boiling point elevation, that's going to equal KBM, and the freezing point depression will be delta TF equals KFM. The labels are both degrees Celsius, so that's going to be the boiling point elevation and the freezing point depression. Those are two very important equations. What we're going to go over now are some of the equations. Here is another shot of the precipitating out of solution potassium nitrate out of a supersaturated solution. That's a little bit better shot of it. It's actually kind of neat. A saturated solution has the same rate of precipitation and dissolution. So for every molecules that's dissolved, something becomes undissolved or precipitates. And so the dissolution process is actually an equilibria problem or phenomena, where some things are going to be undissolved and some are going to be dissolved. Here is a saturated solution. Saturated concentration, solubilities depend strongly on temperature. We saw this a little bit before. Look at potassium nitrate. It goes from around 12 grams per 100 grams of solvent at 0 degrees to well over 242 grams per 100 grams of solvent. That's actually pretty close to what it should be. Don't ask me why I know that. Gases dissolve in liquids like solids, but usually have much simpler behavior. For example, gases are less soluble at a high temperature than at low temperature. So the carbon dioxide, which is not listed here, would be less soluble at high temperatures. Thereby the warm soda will overflow and bubble out more quickly than cold soda. Here is a relationship between pressure and solubility. The solubility of a gas depends on its partial pressure above the solution. So as I increase the pressure, P2, I'm going to increase the solubility. That's actually a law that we'll look at in a little bit, but that's true. That's consistent with the laws on solubility of gases in a liquid solvent. The vapor pressure of a solvent depends on how pure it is. Here we have solvent molecules in A and the non-volatile solute molecules in B. Which one do you think has the higher vapor pressure, A or B, and why? So we know that vapor pressure of a solvent depends on how pure it is, but how is it dependent? How is it dependent? How is one dependent on another? The addition of solute raises the boiling point of a solvent. The addition of solute lowers the freezing point of a solvent. There's a triple point diagram, and that will show you graphically how that's true. So the addition of a solute raises the boiling point and lowers the freezing point. Boiling point elevation and freezing point depression. And osmosis is the movement of solvent through a membrane to equalize concentration on both sides. And you can see how you start where it's even, and then the osmotic pressure increases, and on the right side is going to increase. Then you apply pressure needed to prevent volume increase on the right. So osmotic pressure, such as in dialysis, the pressure required to allow for no transport of solvent across the membrane is called the osmotic pressure, and obeys the relationship of N solute, moles of solute over volume of solvent, times RT equals MRT. M is going to be the moles of solute over the volume of moles of solute over the volume of solvent. Osmotic pressure has a great effect on living cells because their walls are a semipermeable membrane. Here I have A. The crenation is caused by water movement out of a cell in hypertonic solution. Hemolysis is caused by movement into a cell in a hypotonic solution, as listed above in A and B. Most excellent site for visuals of solution chemistry, and that's going to be chem.ufl.edu. So that's a very good source that I utilized to come up with some of those illustrations. Here I have the interaction, ion-ion down to London dispersion, and how I have examples and the energy changes that occur as a result of that in kilojoules. The distance between the ion center and negative pole of dipole. Here is water and a rather large ion, and the distance is measured. Factors that can influence the strength of intermolecular forces, identity of interacting molecules, distance between interacting molecules relative to the hydrogen bond, relative orientation of interacting molecules, how are they oriented relative to one another, and location of molecule in a liquid or a solid state. London dispersion forces, LDF, also known as dispersion forces. London forces, instantaneous dipole-induced polar forces, or loosely van der Waals forces, are a type of force acting between atoms and molecules. They are part of the van der Waals forces. The LDF is named after the German-American physicist Fritz London. London forces became stronger as the atom in question becomes larger, and to a smaller degree for large molecules. This is due to the increased polarizability of molecules with larger, more dispersed electron clouds. This tendency is exemplified by the halogens from smallest to largest, F2, Cl2, Br2, and I2. Fluorine and chlorine are gases at room temperature. Bromine is a liquid and iodine a solid. The London forces also become stronger with larger amounts of surface contact. Greater surface area means closer interaction between different molecules. So the London forces are going to be responsible for, in the halogens, bromine a liquid at room temperature and iodine a solid at room temperature. Here is an example of hydrogen bonding where I have a kind of a dipole set up. I have the positive end of the water molecule and the negative end of the water molecule, and things lined up relative to the orientation. I have concentration. In chemistry, concentration is the abundance of a constituent divided by the total volume of the mixture. Definitions: solution, homogeneous mixture; solute, substance being dissolved; solvent, present in greater amounts. Sometimes that's the only definition for solvent. Qualitative descriptions: these glasses containing red dye demonstrate qualitative changes in concentration. The solutions on the left are more dilute compared to the more concentrated solutions on the right. Qualitative description continued. Often in informal, non-technical language, concentration is described in a qualitative way through the use of adjectives such as dilute for solutions of relatively low concentration and concentrated for solutions of relatively high concentration. To concentrate a solution, one must add more solute, for example, alcohol, or reduce the amount of solvent, for example, water. By contrast, to dilute a solution, one must add more solvent, or reduce the amount of solute. Unless two substances are fully miscible, there exists a concentration at which no further solute will dissolve in a solution, unless, of course, it's saturated, unless, of course, it's supersaturated. So there's a connection among the terms: concentrated, saturated, supersaturated, dilute. At this point, the solution is said to be saturated. If additional solute is added to a saturated solution, it will not dissolve, except in certain circumstances when supersaturation may occur. Instead, phase separation will occur, leading to coexisting phases, either completely separated or mixed as a suspension. The point of saturation depends on many variables such as ambient temperature and the precise chemical nature of the solvent and the solute, such as water has a nature. Here's concentration. There's percent volume, percent mass. Notice its volume of solution is in the denominator and mass of solution in the denominator, which is a very important distinction, as opposed to mass of solvents or volume of solvent in the denominator. So those are two examples of how concentration can be calculated, and a must-know for any problem in the back of the book. Here is molarity and molality. It's both, the numerator are moles of solute, but in the denominator, the molarity is volume of solution, and for molality, it's mass of solvent. It's 1 kilogram of solvent, as opposed to molarity, which is 1 liter of solution. 1 liter of solution. Henry's law relates solubility to pressure, just as in Gay-Lussac's law or Charles' law, where you have a direct relationship. The solubility of a gas is proportional to the pressure. Here's mole fractions, and then you have another one where you have dilutions, and the solubility, mass solubility, is going to be the mass of solute in 100 grams of solvent, or sometimes 100 cubic centimeters of solvent. Here's a better example of hydrogen bonding, where you have that lone pair of those 2 lone pairs of electrons that are going to create this these areas of partial negative dipole, and then it will attract other water molecules, creating surface tension and needing a surfactant, possibly, as in laundry. Here is a relationship which looks at changes of energy, lattice energy, heat of hydration, heat of solution. Very important in the study of thermodynamics, where you have, is the overall reaction going to be exothermic or endothermic, and why, when you sum the reactions, and can you sum the reactions. Here is diffusion and osmosis. And how do they compare? Well, equalizes the concentration of two solutions. So that's where it's connected for diffusion and osmosis. Here's a great shot of the colligative property osmosis. You have salt water and fresh water, and you have the semipermeable membrane, hydrostatic pressure equal to osmotic pressure. Very important in the Middle East, where you have water desalination produces fresh water in this way using osmotic pressure variations. Here we have how sugar dissolves in water. Remember, sugar is being solvated, it's being surrounded by the water molecules, and the molecules of sugar are small enough that they can be suspended, essentially suspended by the water molecules and form a stable solution as opposed to a suspension. Now remember, the sugar molecules do not dissolve. They dissolve, but they do not ionize. Here I have soap. Soap is dissolving the oil on your hands with the nonpolar end, and then you have the water dissolving in the ionized head of the soap. Here's another example of a micelle, where you have this kind of emulsion that occurs. You're emulsifying the grime and getting it off your hands. Here's fabric softener, rearranging the hydrogen bonding, making the hydrogen bonding more ordered, making the fabric softer as a result of the addition of the fabric softener. Why wrinkles? Water is the key culprit behind wrinkling of cellulose-based fabrics such as cotton, linen, and rayon. The polymers in these fabrics are linked by hydrogen bonds, which are the same bonds that hold together water molecules. Absorbent fabrics allow water molecules to penetrate the areas between the polymer chains, permitting the formation of new hydrogen bonds. The new shape becomes locked in as the water evaporates. Steam ironing works well on removing these wrinkles. Permanent press fabrics. In the 1950s, Ruth Rogan Benarito of the Department of Agriculture came up with a process for treating a fabric to render it wrinkle-free or permanent press. This worked by replacing the hydrogen bonds between the polymer units with water-resistant cross-link bonds. However, the cross-linking agent was formaldehyde, which was toxic, smelled bad, and made the fabric itchy. Plus, the treatment weakened some fabrics by making them more brittle. A new treatment was developed in 1992 that eliminated most of the formaldehyde from the fabric surface. This is the treatment used today for many wrinkle-free cotton garments. Modern wrinkle-free fabrics still pose issues of durability, which is why they are often combined with sturdy, flexible synthetic materials like nylon. Got a question about today's news? Ask the explainer. Explainer thanks Janet Brady and Nancy Howard of Philadelphia University and Brent Smith of North Carolina University. That's where I got this information from. Heat and water, the science of wrinkles. The interaction of heat and water with a fiber's molecular structure causes wrinkles. Not all wrinkles are the result of pressure, and some wrinkles are more likely to wrinkle than others. In addition to the weave and thread count of a textile, the fibers manufacturers use to produce fabric can affect how a garment will wrinkle. Cellulose-based fabrics like cotton, linen, or hemp are particularly absorbent. When exposed to water or sweat, the fibers will absorb the moisture, causing the fibers' hydrogen bonds to shift position. When the moisture evaporates, new hydrogen bonds will form and set creases in place. So blame the water next time you're criticized for wrinkly clothes. Heat from washing, drying, or even from the body can also break up the molecular structure of fibers, causing wrinkles to appear where molecules have formed new bonds. Textiles from animals like wool or cashmere are less likely to wrinkle because their fibers are more elastic. Wrinkles can, however, be removed by ironing, and iron's heat and moisture can reverse the wrinkling process, locking in the polymers while the iron's pressure ensures a crease-free finish. Textile producers can alter the molecular structure of fibers to produce fabric for permanent press or wash and wear garments, and that is from the World Wide Web. So look at the link. Very, very informative. Wrinkle-free world, how permanent press can cause permanent damage. In a world full of packed schedules and lives lived on the go, it is easy to see why many would argue against getting organic and natural clothes based on convenience. And while permanent press came into our lives in the 1950s to ease the burden of the overworked housewife, the expense of that convenience is often a toxic-filled one. First, let's talk about what causes those pesky wrinkles using cotton materials as a prime example yet again. The wrinkles in cotton are caused by the relatively weak cross-linked hydrogen bonds that keep the cellulose polymers in place in cotton materials, as well as hemp and flax, which are competitors with cotton for clothing. These hydrogen bonds are broken by moisture, and when the fibers shift to realign themselves, a wrinkle is born. In the 1950s, researchers at the USDA Southern Regional Research Center developed a practice to produce our wrinkle-free and wrinkle-resistant clothes by replacing the weak hydrogen bonds with stronger bonds that were water-resistant. The secret weapon in their war against housework? Formaldehyde. They don't use formaldehyde anymore in the laboratory because it's a carcinogen. Formaldehyde is a very simple organic compound, which is a carcinogen, means it can cause cancer, and it is very toxic. And it used to be used in the clothing industry. That's right. The key to keeping your wardrobe smooth and wrinkle-free is often a known carcinogenic that may cause a variety of health complications, including burning and watery eyes, respiratory complaints, for instance, coughing and difficulty in breathing, and allergic contact dermatitis in some consumers. Even as producers are more aware of the danger of applying toxins in their processes. The principal concern with this treatment was the smell it left on the clothing. So in the late 1990s, the process was improved to nevertheless include formaldehyde, but to reduce it so as not to irritate the delicate nose. You can find two techniques of creating permanent press clothing that are now being actively applied. The first consists of soaking conventional cotton material, formaldehyde resins, rolling the toxic fabrics between huge rollers to squeeze out excess resins, and then baking the fabric in large ovens at 300 degrees Fahrenheit to essentially cure the resins to the materials. This baking approach ensures that the toxic formaldehyde becomes permanent in the fabric and can't be washed out. Some apparel suppliers take it one step further and treat the baked-in formaldehyde apparel with liquid ammonia to lessen shrinkage. Who would have ever thought that clothing can cause cancer? The other approach on the war against wrinkles that is actively being utilized consists of exposing garments to formaldehyde gases, which then permeate the material and are then baked into the clothing, commonly referred to as vapor phase technology. This process places fabrics in airtight chambers and moistens them with water or steam till the moisture is anywhere from 5 to 20% of the material weight. Formaldehyde gas is then pumped into the chamber till the concentration of air from the chamber is approximately 40 to 60% formaldehyde gas. It's unbelievable. Remember, formaldehyde is a carcinogen. To make the formaldehyde link and bond with the hydrogen atoms inside the material, sulfur dioxide gas is also pumped in to the chamber, making a nice little chemical sauna to create your wrinkle-free material. A variation on this strategy involves soaking the fabrics with an aqueous solution of a weak acid salt, just like ammonium chloride or phosphoric acid, after the fabric has been exposed to formaldehyde to facilitate additional efficient cross-linking. So not only are we talking about formaldehyde, but sulfur dioxide, ammonium chloride, phosphoric acid, and probably a variety of other chemicals that are not even listed. And although producers may vary what chemicals are utilized as being a catalyst or temperature in the gas chamber, it is nevertheless easy to see that the course of action of creating effortless care garments is anything but easy. It involves higher doses of chemicals and is technology intensive. Never mind the fact that growing cotton itself is a chemical-laden method, but to continue to saturate the fabric in chemicals is often a higher cost on both the environment and the consumer. So what is someone supposed to do? The growing of cotton is labor intensive, is technology intensive, is chemically intensive. Then the production of the fabric, which is often done outside the United States, for instance, where you have quality controls, and who knows what goes on. Here is nylon 6 and nylon 6,6, and there's the repetitive link of the polymer N. Wrinkle-free world continued. Natural clothing nowadays is becoming far more mainstream, along with the excuses not to buy them are growing slim. Bamboo fibers, if grown and processed responsibly, provide an excellent organic alternative for your wardrobe and household. Whether you're searching for a bamboo sheet set, natural duvet covers, or organic women's apparel, there are stylish and inexpensive options for you. So, my point being that every country has a single set of quality control measures that it applies to industry. And some countries are better than others. Where you have poor quality control, where clothing crosses borders, it's difficult to know what country to trust relative to buying clothing in terms of its origin. And if you dread the iron as much as the 1950s housewife, not to worry. Bamboo fabrics are still silky, lightweight, and with a few shakes are as wrinkle-free as permanent press. And the article source is listed there. Pretty amazing stuff. and consistent with the other sources that we looked up relative to wrinkle-free material. Here's a fat molecule treated with acid, and we have 3 fatty acid soap molecules. So if you have one fat molecule, which is a triglyceride, and you apply soap, you can get 3 times the amount. What effect will softener use have on absorptivity? Well, without it, you have it on the left. Everything is a little bit crazy, and on the right, it's much more organized. If Ruth R. Benarito, who passed away on October at age 97, had been around to see the media coverage of her death, she would have likely been dismayed. News outlets such as the New Orleans Times, Picayune, Benarito's local paper, proclaimed in obituaries that the chemist's research team had discovered how to make wrinkle-free fabrics during the 1960s. The misconception that Benarito invented wrinkle-free fabrics all by herself began to propagate in 2002 after she received a Lemelson MIT Lifetime Achievement Award for work she carried out at the Department of Agriculture Southern Regional Research Center in New Orleans. Her name was Ruth R. Benarito. A local reporter was incapable of understanding the fundamental physical chemistry work Ruth did and got the story wrong, says Benarito's former colleague and friend, Noelle Bertonieri. You can also see in the red there's hydrogen bonding, so it's more than just as in water. Hydrogen bonding occurs elsewhere. In reality, the concept of giving unruly fabrics, such as cotton, a wrinkle-free finish arose during the 1900s in Europe. Scientists recognized that this natural material is made of numerous parallel chains of polysaccharide cellulose, and that those chains are held together by weak hydrogen bonds. When a cotton garment is left sitting in the dryer, the bonds break and eventually reform as the cellulose chains shift into new kinked configurations called wrinkles. To deal with this insubordinate behavior, chemists began treating fabrics with molecules that cross-link the cellulose chains to permanently lock them into place. So these disaccharides, for instance, like sugar, we'll get back to that in a moment, tying up cellulose with urea formaldehyde and other cross-linkers gave cotton memory, says Ken Greason, senior textile chemist at Cotton Incorporated, an industry-sponsored research and promotional organization. But the treatments to flatten out cellulose made cotton fabrics brittle. In those early days, up through the 1950s, Bertonieri says you could sit down and your shirt would rip across the back. Sometimes the treatments even caused color changes in garments. If you bleached something with chlorine and then ironed it, it would yellow very badly, Greason says. Sugar is sticky because of hydrogen bonding. We'll get back to that. That's because the chlorine reacted with amine groups in the cross-linkers. It was at this point that Benarito's team and other research outfits stepped in to smooth out the chemistry. By the 1960s, cotton apparel and fabrics accounted for 78% of the textile market. But the popularity of synthetic, wrinkle-free fibers such as polyester was causing that market share to slide, worrying the cotton industry and driving researchers to seek ways of making cotton easier to care for. One answer was dimethylol dihydroxyethylene urea, DMDHUE. This cross-linker has 4 hydroxyl groups capable of forming tight covalent bonds to cellulose. That's dimethylol dihydroxyethylene urea. Amazing chemical. This cross-linker has 4 hydroxyl groups capable of forming tight covalent bonds to cellulose. Just said that. All of those links have made DMDHEU a workhorse finishing agent in the cotton industry today, says Charles Q. Yang, an emeritus professor and textile expert at the University of Georgia, Athens, outside Atlanta. But because the compound modifies cotton in the presence of an acid catalyst, it also weakens the fabric, he explains. Another downside of DMDHEU is that over time it can break down and release formaldehyde, one of the starting materials used to make it. Again, we're back full circle to formaldehyde. So if it's not a urea compound, it is formaldehyde. So you can't win. Although formaldehyde is a naturally occurring substance, even an apple contains up to 20 parts per million of the stuff, Greason says, with significant exposure, it is deemed a probable carcinogen by the Environmental Protection Agency, which is a federal agency, the EPA. According to the Occupational Safety and Hazard Administration, OSHA, inhaling 100 parts per million of the chemical is immediately dangerous to human health. So the textile industry has voluntarily lowered the levels of formaldehyde on garments by capping DMDHEU with molecular groups such as alcohols. In 2010, the Government Accountability Office, the investigative arm of Congress, conducted a study on levels of formaldehyde in garments. So now they're capping the DMDHEU with alcohols. Of 108 items tested, only 10 of them contained more than 75 parts per million of the compound, no doubt thanks to low formaldehyde formulations. Still, some experts would prefer formaldehyde-free crosslinkers. I wear polyester, Yang says. He doesn't like the idea of formaldehyde being next to his skin or transferring to other garments in his closet. Yang has helped develop carboxylic acid crosslinkers and is waiting patiently for manufacturers to get on board with using them. The Southern Regional Research Center patented these types of modifiers. The problem with the formaldehyde-free linkers is that they require a higher reaction temperature than DMDHEU and are more expensive. Surely that expense would come down if they're widely marketed. Another challenge is that the catalyst used with the carboxylic acid linkers, sodium hypophosphite, can diminish some garments' color, Greason says. DMDHEU has 50 years behind it, so you can imagine it's an uphill battle trying to come up with something that'll outperform it. And that concludes our lecture on solutions. I will post the problems, the answers to the problems from acid-base chemistry, hopefully by tomorrow at the latest.